Okay, so we were saying that when we want to calculate the characteristic lengths, we should consider the whole surface, okay? Not part of it. It's true that they asked per meter, but if you have a rectangle of 1 meter width, okay, and you want to do its analysis, you take the characteristic lengths for 1 meter and for W. But here you want the characteristic lengths for an infinitely long rectangular duct. So the characteristic length is based on the actual geometry. And after, to find the heat per unit length, then you calculate Q and you divide by L, okay? To have the flux per unit length. We'll see how, okay? But when you calculate H, in order to find H, you need the characteristic length. And here you want to have H bar, H average for the whole surface. Since you are searching for H bar for the whole surface, then you need to consider the characteristic length for the whole surface. And here it's an infinitely long duct. You have a very long duct of length L and of width W. And whenever L is very large, when the length is when you have a very high length compared to W, you can simplify a little bit the characteristic length. Why? Because what is the formula of characteristic length? The characteristic length is the area of the horizontal surface. And if you have here a rectangle, the area is W times L, okay? While the perimeter is 2L plus 2W. Okay. Now, when they tell you very long, and if you have a very long duct, this means that L is very large compared to omega. Okay. So when you say 2L plus 2W, you can consider that 2W is really small compared to 2L, so I can neglect it. And when I neglect it, I can simplify L. Okay. So for a very long duct, I can approximate the characteristic length by W over 2. Okay, so keep in mind the characteristic length, you get it for the whole surface that you have. And since here it's a very long duct, the characteristic length will be equal nearly to W over 2. And once you get the characteristic length, you can replace in Rayleigh formula. You replace in Rayleigh formula, and you will get for your top and bottom surface for both, it's same L, same characteristic length, because same geometry. So for both, you have same Rayleigh, which is 1.38 times 10 to the power 8. But what will be different for the two is the formula of H bar, the average convective coefficient. Why? Because we said we have two cases, top hot surface, okay, and bottom hot surface. So to know which formulas to use, I look at Rayleigh value. It's nearly 1.4 times 10 to the power 8. I go to my slides, these slides, okay? 1.4 times 10 to the power 8. If I have the surface, I am in the case of hot plate, okay? I want first lower surface of hot plate. For lower surface of hot plate, which is the bottom surface, since Rayleigh is in the range, it's 1.4 times 10.8, Elna? 10.8? Yes, I think 1.4, 10.8. So it's in this range, and the Prandtl number is 0.71, so we can apply these relations. So for the lower surface of hot plate, we need to use this formula, okay? While for the upper surface of hot plate, Rayleigh is in this range, okay? It's larger than 10 to the power, so we should use the following formula, okay? And now, once we determined the formulas to be used, we can go back to our problem. Okay, and we replace in the formulas. We replace in the formulas one time for case of top, one time for case of bottom, and we get the corresponding value. As I told you, you have several possible formulas. Sometimes I give you a set of relations. More than one can be applicable. You can select any one that is applicable to your case. Okay. Now, once we are done with this step, we can calculate now the total heat loss. What is the total heat loss per unit length? So if we go back to the formula, okay, what is the Q actually? Q is 2 times H vertical times vertical area times delta T. Okay, so this is the loss from vertical areas plus H bottom. Of course, I talk about H bar average value, H bar vertical, H bar top, H bar top times area top times delta T and plus H bottom bar times area bottom times delta T. But since they want us to find per unit length, Q prime, you know that Q prime is Q over L. Okay, so it's A vertical over L, A top over L, and A bottom over L. For example, if you take the top, what is area top and area bottom? Area top equal area bottom equal W times L. And when you divide by L, L will cancel out. L will cancel out. Okay. Now, for the vertical, area vertical, so for the vertical sides, what do you have? You have the height. This is the vertical area. Height times L. So equal H times L. And when you divide by L per unit length, you just have H. Okay. That's why, as you can see, they took delta T into factor because delta T is the same everywhere. It's T surface minus T infinity plus 2 times H bar vertical surface times the height plus H bar top times W plus H bar bottom times W. And now you have calculated all values of H bar. You replace them in your formula. You get the total heat loss per unit length. Okay? Clear? Question on this? So as you can see, it's really simple. The whole challenge is to find H, and you need to determine what is the type of surface. You go to the appendix, you select the appropriate relation to use. Another example, a horizontal uninsulated steam pipe passes through a large room whose walls and ambient air are at 300 Kelvin. The pipe of 150 millimeter diameter has an emissivity of 0.85 and an outer surface temperature of 400 Kelvin. Calculate the heat loss per unit length from the pipe. Okay, so in this problem, we have the following. Let us do a small figure. Okay, we have a circular duct. The diameter is given. We have the condition at surrounding. So we have walls. They gave us walls at temperature 300 Kelvin and quiescent air at 300 Kelvin. So here you have heat loss from the cylinder by two processes. You have radiation with walls, and this is why they gave you the emissivity of the surface. And you have also convection. You are very familiar with this type of problems. We did it in previous chapters. But what is new here is that before they gave you H, they tell you we have air with convective coefficient H equal this value and T infinity equal to a given value. Here They didn't give us H. This is the new thing in this problem. H is not given. And because they said quiescent air, this means that we are in the case of natural convection. So we should use the formulas for natural convection. Okay? Now, first, we need to determine what is Q prime, the heat loss per unit area. Q prime is Q over L. Okay? And we know here that the losses can be divided into two parts. We have Q radiation plus Q convection. Okay? Now, can you tell me what is the expression of each of these losses? What is Q radiation by definition? Who can tell me? What is the formula for Q radiation? You have the emissivity, epsilon, times the Boltzmann constant. What is the area of exchange here? The lateral area of your cylinder. Okay? What is the lateral area of your cylinder? You have pi dl. Okay? Times what? Times T surface to the power 4. Pay attention to use temperatures in Kelvin. T surface to the power 4 minus T infinity to the power 4. Okay? Now, what about Q convection? It's a plus H bar. H bar is to be determined from this chapter. This is what we will learn in this chapter. How to find the value of H. So H bar times also the area of convection is the same as the area of radiation. It's pi dl. Pi dl. Okay? Times delta T. So times T surface minus T infinity. We have everything in this formula except H bar. Okay? Of course, we don't have L because we need to do it per unit length. And if you divide by L to get Q prime, you should divide by L. L will be simplified. That's why you don't need the value of L. Okay? So, to be able to calculate Q prime, we just need H bar. How to find H bar? We should look at the geometry of the figure. What do we have here? We have a very long horizontal cylinder. Okay? Very long horizontal cylinder. So we go to the slide, to our slides to see what is the formula for a very long horizontal cylinder. Okay? So this is the formula for an isothermal cylinder. Churchill and Chu recommended a single correlation that is applicable for a wide range of rays. So, or we use this relation, okay? Or we can use a more specific one. So we should look if we have other relations. We have other relations, okay? So try always, if you find a specific relation, try to use it because it will give you better accuracy. So here, what you should do.
دكتور
Yes?
إذا بالإكزام مثلا ما انتبهنا إنه في واحدة more accurate واستعملنا هديك صح؟
اوكي بلا لازم تنتبه لانه you should look at all. انا بعطيك appendix. Okay, I will give you an appendix in the exam. You should try in your appendix to use the most accurate one. I will not count it as wrong completely, but يعني you will lose a certain some points because it's better to select okay a specific range. And whenever you have a value that's specific, it's better to go for it. Okay, بس مثلا if you have if you don't find the range of interest in your case in this table, you can try to go to the wider formula, to a formula that will always work. Okay, so here we have depending on Rayleigh value they gave us what should be C and what should be N. So if you look at the following relation, Okay. Nusselt average is equal, of course, for a cylinder, for a horizontal cylinder, the characteristic length is the diameter. It's D. Okay. And the conductivity K is the conductivity of air at which temperature. Also here they mention for us that the reference temperature, so we evaluate K at film temperature, T film, which is T surface plus T infinity over 2. Please pay attention. Conductivity of what? Of the fluid. Okay, not of the material of the duct or of the rod. Okay, so T film is T surface plus T infinity over 2. And we go to table, if here the fluid is air, we go to table of air. We see at this temperature, which is the film temperature, what is the conductivity of air. Okay, and then we calculate Rayleigh number, and for the value of Rayleigh that we get, we decide, depending on the range, we decide what are the values of C and N to put in this formula. Okay, so we will use this formula, and we should check for Rayleigh to know which coefficients to use. Let us do it. Okay, so first, as we said, we go to table of air. And at film temperature, which is T surface plus T infinity over 2, we find all properties needed, mu, K, alpha, Prandtl, beta, etc. Okay, we find them from the table. Next step, we do the analysis that we did together for Q prime. Q prime is equal, as we said, to Q prime convection plus Q prime radiation. So we evaluate the Q prime. And next step is to calculate Rayleigh. In Rayleigh, we need the characteristic length. For the characteristic length, which is of a cylinder, horizontal cylinder, it's the diameter D. So we replace first beta, mu, and alpha. We got them from the table. We replace them. Ts minus T infinity are provided. We have everything. We calculate Rayleigh number. Rayleigh number is here 1.511 times 10 to the power 7. Here, as you said, we have several approach. Or we go to the table and find C and N for this range. And for 10 to the power 7, we are above 10 to the power 7. We are here in this range. So we can take C to be 0.125 and N to be 0.333. Also, another approach will be also a possibility is to use this formula, okay? Because the Rayleigh number is smaller than 10 to the power 12. But if we have the choice between these two, this is better because this is more specific, okay? This is more specific. And we might have other relations, okay, also. So it depends. You look in your appendix and you select the most appropriate one. Okay, so now we got from the empirical relation what is Nusselt. Once we got Nusselt, we say H bar is Nusselt times K over D over the characteristic length. We get H bar. And now we are done. All we have to do is to replace H bar in this formula to calculate the value of the heat loss rate. Okay. Question on this problem? Okay, another problem. A glass door fire screen used to reduce exfiltration of room air through a chimney has a height of 0.71 meter and a width of 1.02 meters and reaches a temperature of 232 degrees. If the room temperature is 23 degrees, estimate the convection heat rate from the fireplace to the room. So here we have a glass door. It's in a vertical position. So we are in the case of a vertical surface. Okay, they gave us the height. And you know, for a vertical surface, the characteristic length is the height. So we don't care for the characteristic length, we don't care for the width. We just care for the width. You know why? Because they said to find the heat rate of convection. How to calculate the heat rate of convection by definition?
هي Q second times area.
Yes. يعني هي HA delta T. So why we need the widths? Because to calculate the area. But we don't need the widths for the characteristic lengths. Since for a vertical surface, the characteristic length is the height. So here A will be H times W. Delta T is 232 minus 23. And we just have to calculate now H bar. And since it's a vertical surface, we say we need H bar vertical, and the characteristic length L to use in Rayleigh number is the height, which is 0.71 meters. Okay. So this is our figure. We need, as usual, we need to evaluate all properties of air at the film temperature for a vertical surface. So we take T surface plus T infinity over 2. We get 400 Kelvin. Sometimes if you don't have it, if it's not present in the table directly, for example, if you have 429, for example, okay, or 28, from thermodynamics, you can do interpolation. And if you have, for example, in the table, if you have values between 420 and 430, let's say, okay, you should interpolate between these two values to get your properties. Okay, and problems will remind you of how to do interpolations. But if you have it exactly, or if it's very close, if it's 421, it's fine if you take it as 420. It's not a big deal. So you can find your properties from your table, K, mu, alpha, Prandtl, beta, etc. Next step, we say how to calculate the heat rate of convection. It's H bar times area of the surface times delta T. And we have everything except H bar. So we need to evaluate H bar. Since we have quiescent air in the room, we don't have forced convection, we need to use natural convection formulas. So we evaluate Rayleigh. Okay, if it's a forced convection, you don't evaluate Rayleigh, you evaluate Reynolds. This is the difference. So here we will evaluate Rayleigh number. Rayleigh number at a certain L, at a certain characteristic length, is G beta delta T L cube over alpha mu. This is also from your appendix. I give you this formula. And you say, since it's a vertical surface, L is the height. Now you have everything. You have beta alpha mu from the table. G is 9.8. T surface minus T infinity, you have the temperatures. You can evaluate your Rayleigh number. You got a Rayleigh number larger than 10 to the power 9. Okay, so this corresponds, it's not a laminar case. You are in the case of transition to turbulence. That's why if you go to your appendix, you can see that for the Rayleigh larger than 10 to the power 9, I can use the following formula. Okay, so all you have to do now is to replace Rayleigh and Prandtl by their values, and this will give you the average Nusselt number. And once you find the Nusselt number, you are ready to calculate H. H bar is Nusselt bar times K over L. And now, once you have H bar, all you have to do is to replace it in. Look, to make sure that your work is right, natural convection is characterized by values of H that are relatively small, between 5 and 10 nearly for air. So if you get a very large value here, you must pay attention that you have a calculation error, because for very large value, you go to forced convection. So it's good to know the range of values of free convection to make sure that your calculations are right. Okay. Now, here we can compare, if you want, once we have H bar, we can compare to make, here we didn't consider radiation, we just considered convection. To make sure if this is reasonable or not, okay, we can compare. So now we have the loss by convection, it's 1060 watt. To make sure if radiation can be neglected or not, we can calculate it. Okay, so radiation heat transfer effects are often important relative to free convection. Let us verify this. If we consider that we have radiation, and if we consider that the emissivity of the surface is 1, because in general, um, in general, in the chimney applications, one of the main mode of heat transfer is by radiation. And this is why when we put here the glass panels that we put for our chimneys is characterized by a very high emissivity in order to transfer heat by radiation to the surrounding. Natural convection will help also. So you have convection and radiation, but radiation will be in general more important. And we can verify this from the calculation because we get from natural convection, the heat is nearly 1060 watt. While if we consider an emissivity of 1, and for the area that we have, H times W, and we multiply by sigma times T surface 4 minus T surrounding 4, if you apply it, you get that Q radiation is nearly 2,355 watt. And this is expected because in general, in case of chimney, radiation will be more important than natural convection. But both, if you want, you cannot neglect any of the two. Even natural convection is relatively high. It's 1,060 compared, so it's nearly 50% of radiation, which is good. So it will help you, natural convection will help into heating your space in addition to radiation process. And the Q total will be equal to Q convection plus Q radiation. Okay. Any question on this? So hence, in this case, radiation heat transfer exceeds free convection by more than a factor of 2. The effects of radiation and free convection on heat transfer from the glass depend a lot on its temperature. Higher the temperature of the glass, radiation will be more dominant. Why? Because radiation is proportional to T surface to the power 4. Okay. While in case of convection, okay, we can by empirical relation will tell us that it's nearly proportional to Ts to the power n, okay, where n is influenced by the effect that we have, because in natural convection you have delta T, but also H depend on temperature. Okay, that's why we can say that for free convection it's proportional to not just delta T, because H also is affected by temperature, and the coefficient is nearly between 1.25 and 1.33, depending on the geometry, depending on the temperature, etc. So radiation is much more affected by the temperature of the surface. That's why higher T surface, so if you increase T surface, the dependence on the radiation will be more and more dominant. Okay, so we expect that the relative influence of radiation to increase with increasing temperature. This behavior can be determined by computing and plotting the heat rate as function of temperature. So if you do Q total for temperature of surface between 50 and 250, you will see that larger the surface temperature, larger the effect of larger the dominance of radiation over convection. Okay. Any question on this? Okay, thank you. Bye.